Hi, my name is Rafael Abrajo. I work at Brookhaven National Lab. I'll be here talking today about quantum astrometry. But before I start my talk, I just would like to thank everybody for being here. I know it's Friday, 8 a.m., first talk in the first section of the last day. So thank you for being here, and also thank you, Chair, and the organizers. All right, so let's first define astrometry. What is astrometry? Astrometry is the measurement of the position and velocity of things in the sky. And why we call it quantum astrometry is because we are applying quantum optics and quantum information techniques to improve astrometric measurements. You guys probably have seen this, which is some of the most famous pictures of recent years astronomy in general, which is the Event Horizon Telescope image of the black hole. Probably everybody has seen it, and if you're in the physics community. And this was only made possible because they used radio waves. If you remember, just from general physics class, like the angular resolution you can see is something like this, the wavelength of the light using divided by the baseline distance you put in. So that's how they done it, and why they use radio astronomy is basically in radio astronomy, you don't need, which I'll be talking in a minute, you don't need to be physically connected to the station. You can record all the information locally. So effectively, you can treat the entire Earth during aperture synthesis as your telescope system. And that's why they achieved this with the radio. In the optical sense, you cannot do it. In the optical sense, because in the optical, I mean visible part of this electromagnetic spectrum and near infrared. Why I mean by that? Because you need a phase-stable optical link between the two baselines. And that needs to be done on the order of magnitude of on the wavelength of light. So the current record for this is Chara in California. And the record, which is the state of the art, is 330 meters. So you see how we went from kilometers and kilometers and kilometers apart to just 330 meters. So that severely limits how you can push the baseline distance and the visible part of the electromagnetic spectrum. All right, about 12 years ago, our community in quantum optics and quantum information start taking a look at this. So this is one of the most important papers in the field by Daniel Gottman, Thomas Genoway, and Sarah Croak, which I'll be discussing some of the key ideas in a moment. So there you still have collecting those ideas, collecting photons for an object in the sky, but you want to create this state where you have a 0 photon in the left hand or 1 photon in the right hand, or you can have the opposite probability, or you can have the opposite state, 1 photon in the left hand and 0 photon in the right hand, and you would have to account for the phase between those things. And if you invert this, which you want to measure the theta, you can get the same equation that we want to do for. So to see this phase, you would need to interfere then in the beam splitter, and that would be the common way you are doing. You're really at the low photon regime. But Daniel and Thomas and Sarah, they went way more further, and they developed this protocol. You basically now have the two baseline stations, but they share EPS, meaning entangled photon source. So you need to have an entangled photon pair shared between this station and this station. And their protocol is to do quantum state teleportation. So in a really simplified way, I would say, what you do basically is you do quantum state teleportation, use the entangled photon pair for teleporting the state from one baseline station to the next baseline, to the other baseline station, then you interfere, then you get the information. All right, it's a very interesting paper. It relies, as the paper say, in quantum repeaters. It's a very interesting, but quantum repeaters is still ongoing research fact, and there's still a lot to be done. The quantum repeaters have been demonstrated at the at some small scale, but the number that you need for implement this is still require much further development. And also, even if you do have quantum repeaters, you have the question, how do you scale that even further? The rates, the things need to work. What about the cost and so on? There's a really interesting talk called Quantum Telescope by Daniel Gottman that you can easily get in Google. Cool. But there is an alternative. And the alternative was developed by my friend at BNL, the post-Tankers, and I will be briefly introducing the idea here. So you still have, this is the fundamental, you still have the two baseline stations separated, but what we want to do is something like this. One photon from that source could arrive either in A or E, and you would create very similar equation that we had the other day, for the other case, or from my previous slide, and another photon from source 2 would arrive between B and F. And then you do a beam split, you're still going to do the interference between those two, interference between here, and you're going to see those outputs are correlated. In fact, what you have created here is a path entanglement. But the question, and there is a thing that I think is important to highlight here. One of the things, this is a two-photon process. So you need to get those two photons to make it, you need to collect two photons, not only one. So you don't need a quantum repeater, but you need to collect one more photon in a simplified sense. So if you see the output is it's going to be something like this. So you see C and G here would be correlated, and you're going to have a factor proportional to the phase difference between those two equations. And you can see the correlated output for a bunch of different outputs combination here. However, in some cases, you will not see. They will be totally canceled out by a Hungo-Mendel effect, which I'll just mention briefly in a moment. And what we also want to do in the last, it's what we call spectral binning, which will be the last part of my talk, so I'll mention that in a sense. So one of the things that, in a very simplified way, is this scheme, which we call SNSV scheme. It's a combination of both the Hamburger-Brown-Twiss effect, actually a variant of the Hamburger-Brown Twiss effect, not the original ATBT, but a quantum variant of this, and the Hungo-Mendel effect. So this is the typical Hamburger-Brown-Twiss interferon we would expect. This is a cartoon-ish version that you can see, like you just separate those things further apart, and you get an intuitive view of what's going on. I just want to mention what is the Hungo-Mendel effect, which is a quantum interference effect. If you have two photons coming, two indistinguishable photons coming out of a beam splitter, you have four classical possible outputs. Quantum interference will happen, and because of conservation of energy, you need a pi phase shift in one of the reflections. That leads to the quantum interference, and the quantum interference will kill those two possibilities, and only you have is those two. So the photons bump together, either arriving at the same, leaving at the same output port. So either this case or this case. So if you do a coincidence detector here, you can see like there's the famous Hungo-Mendel dip, when if you see the time, if you just delay one relative to the other, they will be in the time domain, they will be distinguishable until the same time when they will arrive together, then they are completely indistinguishable. That's when the Hungo-Mendel happens, and you have this dip. And you can see that this is so-called the Hungo-Mendel visibility dip. Because this is a very esteemed audience, I'm gonna just put a side note. This is a previous paper of mine. I'm an experimentalist, but this is a paper that I did previously while I was in Canada. We are all experimentalists, but this is a theory paper, which I like to say is a theory paper about experiment. So it's the quantum metrology time limits that you can do, that you can give in your spectral. If you have a spectral properties of your photons, what is the best Hungo-Mendel you can do it? Please check it out if you're interested. I'm also happy to chat about any of those topics. So simplifying is, this is the SNSV scheme. Just to summarize, we don't need the optical connection. We can enable long distance baseline. And our goal is eventually to use this for many astrophysics and cosmology applications. That's the goal. At the moment, I will not have time to discuss much about the astrophysics and the cosmology applications of it, but improving the angular resolution can lead to a lot of benefits for those two areas, astrophysics and cosmology. All right. So after we done after they did the theory paper, we did the proof of principle tabletop. So it was recently published in the end of last year. So that's feel free to check it out. And I would just mention briefly what we did here. So you can see here the original scheme, and we just use a tabletop version. So you have 2 argon lamps, so it's a thermal light source, and 2 inputs. So it's basically where you're collecting the lights. How am I doing time?
A little over 10 minutes.
Okay, good. I will skip something because of time, but I just want to say we do see the HBT peaks where we expected, so that was a big check. We can see the phase, so this is over time, but at the time our phase was changed, so we introduced a phase delay here between those. So we can see the phase oscillations as we expected. We match it to our theory predictions. So I'll just say the phase oscillation was another cross-check. And also the visibility that we expected also matched our theory. So it was checked. And we did some further work of detecting. Because I'm a little bit on time, I'll just briefly skip the other part. And then on spectral baiting is essentially doing multiple experiments at the same time. So basically each frequency is treated as an independent measurement. We are developing the spectrometer, so the detectors are being developed in partnership with EPFL and Czech Technical University. So we have a linear array of single photon pixels. Each pixel is single photon sensitive. And for a spectrometer, which I skip, you can see our paper in Digital Archive. We can get very good spectral resolution and also very good temporal resolution, which we tested with SPDC source. I just want to highlight one thing. In a different setup, we recently observed frequency resolve HBT up to 5 different frequencies. So that will happen if they have the same frequency, they will have the HBT enhancement. If they're different frequency, they don't. So we did all the frequency collection at the same time, and we see this frequency with this frequency, the HBT happens. This frequency is different. This is the other frequency, the HBT doesn't happen. And we did this at 5 different frequencies. The manuscript is currently under preparation. Stay tuned. I just want to finish highlighting out the team that did the work. It has been a great team, and I really appreciate the effort. So summarize, quantum optics can improve telescopes. We can have many applications in astrophysics and cosmology. And one of the things that we're doing is to develop the new photonics tools that we needed for such a goal. Thank you all, and I'm happy to take questions.
Well, the next speaker, I think Diego can set it up. Can probably have a time for one brief question.
Hi. So,
Hi, Paul.
as the baselines get big, then you